So in example 2, we have a study of U.S. homes using heating equipment. The mean indoor temperature at night during the winter is 68.3 degrees Fahrenheit. You think this information is incorrect. You randomly select 25 homes using the You randomly select 25 U.S. homes that use heating equipment in the winter, and you find that the mean indoor temperature at night is 67.2. So let's talk about what's going on in that part. So there was a random selection of 25 homes. So that's a sample size of 25. And then they tell us that in that sample of 25, the mean came out to be 67.2. So that is the X bar, the sample mean, because that 67.2 came from the sample of 25. From past studies, we do know the population standard deviation of 3.5, so I will go ahead and drop that down here. I'll also go ahead and write down here that X bar is 67.2 and that N, our sample size, is 25. They do tell us that the population is normally distributed, so that's good because 25 is not bigger than 30, but we can still go ahead and use z-scores. Think about what the central limit theorem taught us because this population is normally distributed. So let's go ahead and start writing out. This is a single mean test. Let's go ahead and start writing out our hypotheses because we need to think about what tail test this is. So we have a null hypothesis and an alternative hypothesis. The study of U.S. homes is making the claim that the mean indoor temperature at night is 68.3. Is means equals. So they're claiming that mu is equal to 68.3. I need to put that in the null hypothesis because it has an equal in it. And then you think that this information is incorrect. So you think that's wrong. So if you think that's wrong, you think it is not equal to 68.3. Remember, all these hypotheses need to be the exact opposite of each other. So we have our hypotheses written. Let's go on to step 2, where we calculate our test statistic. Yikes. And we're going to be calculating the test statistic. Remember that this is a z test statistic because we do know sigma and our population is normally distributed. So we're using the formula x bar minus mu divided by sigma over the square root of n. X bar is 67.2. Mu is what's showing up in the hypotheses, that's 68.3. Sigma was given to us as 3.5, and all of this is divided by the square root of n, which is 25. And this comes out to be about a negative 1.57. So now that we know our test statistic, we can go on to step 3, which is where we find our p-value. So I'm going to go ahead and set up the picture here. For a two-tailed test, our test statistic came out to be a negative 1.57, but this test has two tails. So I'm also going to put the positive version of that test statistic, a positive 1.57 on the right. The p-value in this case, I'm going to scroll up to the top to remind us how to find the p-value for a two-tailed test. Half the p-value is to the left of the negative test statistic and half the p-value is to the right. The total p-value area is when we put them both together. So that means that in this picture, our p-value area is the total area that is shaded to the left of this negative test statistic and to the right of this positive test statistic. And remember that this picture does have symmetry. So when I go over to my statistics table and I look up the left area for negative 1.57 and I get 0.0582, that's just for what's over here, 0.0582. Because there's symmetry in this picture, this area on the left here must also be 0.0582. So the p-value is the sum of those two numbers, where we could just doubling it or adding it to itself, because the p-value is the total area that is to the left and the right of those test statistics. So this comes out to be 0.11, I'm going to put a 0 in front, 0.1164. So now that we know our p-value, we're able to go on to step 4 where we make our decision. And the decision depends on what happens when we compare our p-value, which we just found of 0.1164 to our alpha value. And alpha was given to us in the problem as, right here, 0.05. 0.05. So we need to think about which one is bigger and which one is smaller. So here we have 0.05. Well, the p-value is bigger than alpha. That's greater than that. That's a larger number. Going back up to remind us what we do in that case, we're looking at the second scenario here in blue. If the p-value is bigger than alpha, then the decision that we make in step 4 is that we fail to reject the null hypothesis. So now that we have made our decision, let's go on to think about what our conclusion will be. If we are failing to reject the null hypothesis, we are not rejecting the null hypothesis, so we're going to accept the null hypothesis. So we are going to say, remember that we're going to write things in terms of our alternative hypothesis. We're writing to the conclusion in terms of our alternative. So we're not taking the alternative. So we're going to say, there is not enough evidence, or there is not sufficient evidence to support the claim, there's not enough evidence. I'm going to add in here at a 5% significance level. To support the claim that the mean indoor temperature at night during winter, there's a lot of context we need to add in there, is different from 68.3. Okay, I just went ahead and typed it out. So I have, there is not enough evidence at the 5% level of significance to support the claim that the mean indoor temperature at night during winter is different from 68.3 degrees Fahrenheit. And notice that that is exactly written in the terms of the alternative hypothesis, because the alternative hypothesis says that that mean is different than 68.3.